Hello, everyone. My name is Ping Wang. I am from the Department of Computer Science at Virginia Tech. Today, I am going to present our work about self-supervised learning of contextual embeddings for link prediction in heterogeneous networks. First, I will talk about the introduction and the background of this work. Then I will introduce the challenges to solve the problem and further introduce our contributions. After that, I will show the experimental results and then conclude the presentation. Heterogeneous network has a power to integrate large amounts of data from various sources so that the data can be used in a more efficient way. It has been widely used in different domains, ranging from academic co-authorship network, social network, to healthcare knowledge graph. Knowledge graphs can help us build relationships between different entities. It also allows us to discover underlying relations by performing the link prediction task. However, existing link prediction methods only provide a static and fixed embedding for each entity by learning the importance of all semantic neighbors in the graph. They did not consider any contextual information of the downstream tasks. This motivates us to learn the contextual embeddings. Here, I provide an example about the motivation of contextual embedding on academic network. Given two authors published on diverse venues and topics, in order to predict the co-author relationship between the two authors, the state-of-the-art methods aggregate global semantics of nodes based on all neighbors. This motivation for us to learn contextual embedding is that it would perform better if the embeddings for both authors can reflect their common publication topic, representation learning, and venue neurips. The basic idea is that with the global static embeddings, by considering the common topic and venue as local context information, the two nodes in the embedding space will move closer to each other and further produce better link prediction score. However, there are several challenges in learning the contextual embeddings on heterogeneous networks. The first challenge is how to characterize the context. Existing methods define a node's participation in different contexts as facets or aspects, and infer the cluster-driven context for nodes in the downstream tasks. However, many existing works showed that considering higher-order relations over different metapasses or metagraphs is essential for representation learning and link prediction on heterogeneous networks. The second challenge is how to learn the contextual node embeddings so that the embeddings are dynamically changing according to different contexts. The third challenge is how to show the effectiveness of the contextual embedding compared with the static embeddings, and how to interpret the prediction results. In this work, we mainly tackle these challenges. We developed a framework that bridges the static global representation with the localized subgraph-based context to learn the contextual embeddings. Our contributions are in three folds. First, we define and generate the subgraph-based context. The node embeddings will be dynamically changing with different subgraphs. Second, we propose a two-stage approach to learn the higher-order semantic associations by simultaneously capturing the global information and local context. Third, we compare with the static and contextual embedding learning methods and demonstrate the effectiveness and interpretability of the contextual embeddings. Here is an overview of our proposed SLAS framework. There are mainly 4 components. First, based on the prediction task, we generate the subgraph-based context. This will be similar to the semantic context in the natural language. In the second step, we learn the global embedding by considering the node types, relations, and the global network structure. In the third step, we apply multiple contextual translation layers to update the global embedding based on the localized information in the generated context. This allows us to capture the higher order relational dependencies between nodes in the context. As for the learning, we include 2 stages. The first stage is the self-supervised contextual node prediction task. In the second stage, the model is fine-tuned by the supervised link prediction task with more fine-grained context for node pairs. Next, I will introduce the details of each step. For context generation, we explore different strategies for pre-training and fine-tuning. The goal in pre-training is to capture generic node context. So we use a randomized breadth-first search strategy to collect neighbors around each node or random walks with a certain depth. While for the fine-tuning, the goal is to capture context indicating the links between 2 nodes. Since finding passes between 2 nodes in the graph is expensive, we tried both the random strategy and the shortest path between 2 nodes. For each generated context subgraph, we first encoded it as a sequence of nodes and learned their global embeddings that considers various information in the global graph. In our experiments, we mainly considered the global embeddings learned from the random walk-based skipgram methods. The primary step is contextual translation. The goal is to shift the global embedding in the vector space towards the new positions after considering the localized context. We utilize a semantic association matrix to indicate the correlations between nodes in the generated context. It is learned using the multi-head attention mechanism. The changing of this matrix indicates the translation of embeddings according to specific contexts. We consider this as a contextual translation layer, and we can include multiple such layers based on the higher order relations contained in the graph. The updated node embeddings from different layers are aggregated as a contextual embedding. We have 2 learning stages. The first stage is that we pre-train the model with a self-supervised contextual node prediction task. We generate context for each node in the network and randomly mask a node for prediction. The objective is to maximize the probability of observing the masked node based on the context. Then the model is fine-tuned with a supervised contextual link prediction task. We generate context for each node pair and perform the binary link prediction. The objective is to maximize the prediction score of positive edges and minimize the score for negative edges. We used 5 datasets to evaluate the proposed method, ranging from the networks in e-commerce, academic to social networks. We also created a healthcare network about patient medical information based on the public dataset Mimic3. In the experiments, we compare our approach with other methods that learn either static or contextual embeddings. Compared with other baselines, the results show that the contextual embeddings learned from our model can produce better performance on the link prediction task. Here we show the distributions of similarity scores for both positive and negative edges obtained by different methods. We can see that for both baseline methods, there is a significant overlap between the two distributions. This indicates that the embeddings learned from them cannot efficiently differentiate the positive and the negative edges for the link prediction task. Where the slice model increases the margin between the distributions of positive and the negative edges. That means it brings nodes in the positive edges closer and shifts nodes in negative edges farther away in the embedding space. Here we visualize the association matrix over different translation layers for the context generated for paper and an author. It can be observed that the association between both nodes is relatively low in layer 1. However, the dependencies are dynamically updated when applying more layers. Their dependencies become higher from layer 3. This analysis is helpful for us to understand how the global embedding is translated into the localized contextual embedding. Here we show an example of subgraph from DBLP dataset when predicting the link between a paper and an author. We investigated different contexts and found that the link prediction score is highly dependent on the generated context subgraph. If you are interested in our work, you can find more results in the paper. In conclusion, in this work, we developed a contextual embedding learning method for graphs from single relation context to arbitrary subgraphs. Our self-supervised learning-based method allows us to model higher-order semantic associations between nodes. We find that slice contextual embeddings significantly outperform existing embedding learning methods for link prediction on heterogeneous networks. We also found that slice model results are interpretable, effective, and scalable. Our codes are available at this GitHub link. Please feel free to email me if you have any questions and suggestions. Thank you.